Here is an interesting geometry problem. Triangle ABC is equilateral with perimeter 3. We see that here. Since it's equilateral and its perimeter is 3, each side has a length of 1. 5 points are randomly placed in the triangle, or on it, so they could also be on the triangle's boundary. And we're asked to find the probability that 2 of the points are within 0.5 units of each other. So, for example, if 5 points are randomly placed, they could be here, 2, 3, 4, and 5. They could be in the triangle, they could be on the triangle, you could have a point here, here, wherever. And the question is, if we have these 5 randomly placed points in or on the triangle, what's the probability that at least 2 of them are within 0.5 units of each other? The argument we're going to use involves the medians of the triangle. Those are the segments that connect the midpoints of the sides of the triangle. And we'll use the pigeonhole principle. So you can give it a try yourself with those hints if you like. Let's get into the solution. Here is our triangle after drawing the medians. Again, recall that a median of a triangle connects a midpoint of one side to a midpoint of the other side. So now that we've drawn the medians, each side has been split in half, and so all these little pieces have lengths of 1/2. Another result that's important to know is that a median of a triangle, like from here to here, this median, is parallel to and half the length of the third side. This median here that connects this side to this side, it is parallel to and half the length of the third side of the triangle. Thus, each median being half the length of a side which has length 1, each median has length 1/2. So in fact, what we've done by drawing these medians is split the equilateral triangle into all these smaller equilateral triangles with side length 1/2. Now, the pigeonhole principle I mentioned earlier comes in handy. We've got these 1, 2, 3, 4 equilateral triangles that make up the big triangle. The pigeonhole principle says if we have more pigeons than we have holes, there must be at least 2 pigeons in at least 1 hole. In this situation, since we're placing 5 dots in a triangle that's been split up into 4 boxes, so to speak, it must be the case that when the 5 dots are placed, at least 2 of them are in the same equilateral triangle box. In this case, it would appear that this dot and this dot are in or on the same triangle. We might also say that this dot and this dot are in or on the same triangle. No matter how the 5 dots are placed, it has to be the case that at least 2 of them are in or on the same little equilateral triangle. There's just not enough little triangles for any other possibility. And there that logic is written out. There are 5 dots, but only 4 triangular sections, these 4 here. By the pigeonhole principle, at least 1 triangular section must contain at least 2 dots. They can't all be in unique triangular sections because that would require 5 triangular sections, but we only have 4. Now we've almost finished the argument. We know that there must be at least 1 triangular section with at least 2 dots. And that could happen many ways, but we must ask, what's the furthest apart the 2 dots could be that are in the same triangular section? And looking at one of these equilateral triangles, it's clear the furthest apart that 2 dots in or on this triangle could be would be to have 1 dot on one vertex and another dot on the other vertex. This way, they're both on this triangle, but they are as far apart as possible. Any other point in or on the triangle would have a distance less than or equal to this distance. And this distance, like we mentioned earlier, is 1/2. And so that gives us our solution. We were asked, what's the probability that 2 of the points are within 1/2 of each other? Well, we just show that it must be the case that there's a triangular section with at least 2 dots, and the 2 dots in that triangular section can be at most 1/2 away from each other. In other words, it's guaranteed that there are two dots within 1/2 of each other. And that's our concluding argument. Since two dots in the same triangular section are at most 1/2 apart, the probability that two of the points are within 1/2 of each other is 1, because we've guaranteed there will be two dots or points in the same triangular section, and the furthest apart they could be is 1/2. Pretty fun problem that, even though it asked about probability, actually didn't require any probability theory at all. Let me know in the comments if you have any questions or your own solution to this problem, and check the description for my playlist with more interesting math problems. Thanks for watching.
I'm the mathematical menace, the machinations of mankind. Two calculators at the same time, hand signs and abacus, finger count and calculus. I'm a V to the T, my parameter the rapidest. Happens like this, my lecture's the most prominent, dominant. Call me to Morgan, I get the compliments. The union in together like any time that we intersect, cause my opponent